Good afternoon. Welcome to another video lesson for Earth history. Okay, so chapter 5. I'm going to try to squeeze this all in one video, and I'm hoping it can be 30 minutes or less. Otherwise, it will take a very long time to load up to YouTube. All right, here we go. So, chapter 5. Stratigraphy. What does that refer to? It's the study of layered rock. Generally, that's going to be sedimentary rock, sediments, but it's also going to include extrusive volcanic rock, as in lava flows or ash falls from the past. The next two bullets are going to be discussed in the next video lesson, chapter 6. So they look familiar to me already. Of course, you guys probably haven't watched chapter 6 yet, unless you are in the Earth History lab. Okay, so a sedimentary bed is a single layer of sediment or sedimentary rock with a distinct top and a distinct bottom. And then bedding planes are the surfaces that separate adjacent beds. It's basically where you go from, the top of one bed to the bottom of the bed above that. And then if you have more than one sedimentary bed together, you refer to that as strata. I don't have drawings for this because we're going to have some upcoming drawings for unconformities, and you're going to see examples of sedimentary beds and bedding in those upcoming drawings. Okay, in green, unconformities. So this is the first time that we're addressing unconformities. Anybody that took the Earth Science lab in the past, this might be familiar for them. Anyway, it's possible that we will have a take-home quiz dealing with unconformities. I'm not sure yet about that one. So what is an unconformity? It is a gap in the geologic record. A hiatus in material that we feel should be there. So you might think of it as missing rock or missing time. So it's a gap in the record, and this is going to go on for millions to tens of millions of years, perhaps even hundreds of millions of years. Now, unconformities can form due to one of two things. A, erosion. That's the most simple one to imagine and the most likely scenario, I think, a lot of times. Just saying that this rock that you're missing probably was there in the past, but it was eroded away before this younger rock was put on top, and now you have a big gap in the time. What are examples of that? Well, we're going to get to that. There's going to be 3 types of unconformities, so we will have drawings coming up to help explain this. The other possibility for why you have an unconformity or gap in the record is a period of non-deposition, which says that in this location, maybe it was an arid region, and maybe you had a little bit of sand blowing around, but you just didn't have a lot of new material being deposited for a long period of time. So erosion or non-deposition, those are both possible hypotheses for why you have an unconformity. But again, I think that erosion often is going to be the more likely cause. All right, moving over. It's Monday. I always film on Mondays, and I teach 4 classes before I film, so I'm a little tired. Besides, sitting here on the table filming is probably better than standing, and maybe I hold the camera a little more still, and I refuse to use my tripod. All right, 3 types of unconformities. You're going to have a disconformity, you're going to have a nonconformity, and you're going to have an angular unconformity. All right, so we're going to go through all 3. We'll begin there with number 1. A disconformity is an unconformity or missing rock, missing geologic record in a sedimentary sequence. In other words, this is occurring within layers of sedimentary rock, and the units or rock layers are parallel to each other. So let's look at that drawing. And what do we have going on there? Well, we have sediments on the top, which we expect to find. We don't always have sediments covering the rock, but we expect to have that be the case. And below that, we have a rock that's 65 million years old. Below that, we have a rock that's 70 million years old. Those are close enough in age that we might consider them to be conformable, meaning that we're not missing any rock. But below that, on the bottom, I forgot to give, well, I didn't give any of them a rock type. Let's say below that on the bottom is, I don't know, an old sandstone, 300 million years. So notice we have quite a big gap there from 300 million years to 70 million years. That's a long time frame. Okay, so chances are we had rock there in the past that eroded away, and then beginning 70 million years ago, we had younger stuff deposited. Now that thick, dark, squiggly line there between the 300 million year old rock and the 70 million year old rock, that's how we show unconformities, with a thick, dark, squiggly line. Okay, so that is a disconformity. You have a gap in the record between sedimentary layers that are parallel to each other. All right, second one is a nonconformity. So this one might be a bit confusing because you might think it's just another igneous intrusion. We're going to talk about that. This is an older igneous intrusion. Okay, so a nonconformity is your gap in the geologic record, missing rock, between older igneous or metamorphic rock on the bottom and younger rocks above it. So what do we have going on here? Well, we have this granite body that's 500 million years old. And it's very much in the shape of a pluton, and we know that granite, well, that's, an igneous intrusion. So there was rock present here when that granite intruded into it. Now the granite is 500 million years old. The problem here is that the rock layers the granite is punching into are much younger. You've got one there that's 60 million and one that's 55 million. Okay, and notice that I did not draw a zone of contact metamorphism. In a previous lesson, I can't remember which one, maybe it was chapter 4, I use little X's around the intrusion to show the zone of contact metamorphism. Hopefully you remember seeing that either in class together or on a video lesson. We don't see that here. So even before we send these samples for radiometric age dating, we have an idea that granite is not younger than the rocks there in the background because it did not metamorphose that rock. So what happened here is that there were rocks present prior to 500 million years ago. This magma body intruded into those rocks, cooled to form this granite pluton. The material that was on top of that since eroded away, and then this much younger material was deposited on top. That is a nonconformity. All right, let's move on. And I'm going to find a different table to sit on. Okay, so now we're going up here in the orange. Our third type of unconformity is called an angular unconformity. These are pretty easy to recognize, okay? So it's an erosional unconformity on older tilted or folded rocks with younger rocks on top. Again, we're using a thick, dark, squiggly line there to show the unconformity. Let's pan back over to the nonconformity. Same thing there. There's a thick, dark, squiggly line there between the granite, older granite pluton and the younger material on top. Okay, back to our angular unconformity. What do we see here? We see these tilted layers of shale on the bottom. And together, they're about 500 million years old. And then clearly, the material on top, well, there's something going on there. Because that material on top is at an angle. It's not tilted at all. Now, we send this stuff for radiometric age dating, and we see that the shale, well, it was deposited pretty quickly, these layers, around 500 million years old. And when they were deposited flat, horizontally. And then a mountain building event happened. The shale was tilted at an angle. And then erosion took away material on top, and much younger sediments were deposited on top. So again, you see a jump there in the geologic record from the 500 million year old shale to the rocks above it that are 45 and 40 million years old. So those are the three types of unconformities. All right, next. Okay, so now we're going to switch gears a little bit, and we're going to start talking about fossils. Fossils are so much fun. And in a normal semester, as in prior to, the pandemic, I would pass some of the fossil samples around in class for you guys to get to look at them. Of course, that is not going to happen now. But fossils are still really neat. And for now, we're finally going to touch on fossils. We're going to talk about methods of preservation and types of fossils. So this is fun stuff here, beginning in purple. Okay, so fossils are not found in just any rock. They're mostly going to be found in sedimentary rocks and sediments. Okay? They're never found in igneous rock, certainly not intrusive igneous rock. Now, sometimes you can find some fossils preserved in, say, a layer of tuff, which is hardened volcanic ash from some past eruption, or within a volcanic mud flow. So in those cases, the animals were overtaken by the ash or volcanic mud flow, and they likely died pretty quickly. But that material cooled really quickly, and the fossils were not destroyed. They could be preserved. Occasionally, you might find fossils in marble. Marble is a metamorphic rock. Okay, and generally during metamorphism, the fossils are going to be destroyed. But marble is a low-grade metamorphic rock. Just turning limestone into marble requires, well, the rock doesn't have to be buried to great depth. You need some hydrothermal fluids there. But sometimes in marble, you'll find the fossils preserved. But primarily, fossils are a sedimentary rock and sediment kind of thing. All right, what's important about fossils? Well, they are useful in relative dating, meaning putting things in sequential order. I think you will have a take-home quiz where you might be doing some relative dating, putting things in sequential order. Okay, so living creatures, yes, they're all carbon-based, but the half-life for carbon-14 is short, 5,730 years. So for old fossils, we can't use the carbon dating technique. That's just not going to happen. But, you know, we have studied fossils for decades, hundreds of years, really, and written about them, taken pictures, taken samples, made drawings, and categorized them. So, you know, fossils that you find in rock you're studying, you know, chances are somebody has already written about those fossils and has an idea of when they lived. So that's how fossils can, even in the absence of using carbon dating, fossils are useful in relative dating. Again, sequential order. What else about fossils are cool? I mean, other than they're fossils and they're fun to find. Well, they tell us about the depositional environment. So some examples here. Trilobites, which lived all throughout the Paleozoic, were marine arthropods with an exoskeleton. So trilobites did not live on land. We know that for a fact. Okay, and then T-Rex is a good example. T-Rex was terrestrial. T-Rex did not live in ocean waters. Okay, so we've learned a lot about fossils. We've studied them, and they tell us something about the depositional environment. All right, moving on. Still talking about fossils. Okay, so types of fossils. All right, types of fossils. Fossils can include things like body fossils, which means, you know, actual pieces of the animal, not just traces. Okay, so bones, teeth, shells. Fossils include frozen mammoths and permafrost. There are several frozen mammoths. Unfortunately, most of them are in Russia. Yes, so good luck us getting hold of any of them. I'm sure there are probably some in China as well, you know, various parts of Asia. But it's, yeah, we are just, I don't know that we've ever found frozen mammoths in North America. We did have mammoths in North America. I just don't know that we have any of them frozen in permafrost. Maybe we just don't have enough permafrost over here. Okay, mummification is a type of fossil. So, you know, ancient Egyptians and what they did to their dead rulers after they passed. Trace fossils, of course, are types of fossils. Traces of organic activity like tracks, trails, burrows, feeding, traces, nests, and even fossilized feces, which are known as coprolites. So we talk a little bit about trace fossils in another video lesson. It could have been chapter 4. It could have been chapter 6. I'm not real sure about that. All right. One last bit of notes for this side of the room, then we'll move to the other board. How are we doing on time? We're doing okay. All right, so a little something about the body fossils in particular. So how they form or why they might form, and then different types of body fossils. Okay, so body fossils, well, you're not going to get that kind of fossil for just any species. Okay, there are I'm sure, species that have come and gone that we'll never even know about because none of their remains were fossilized. Guarantee that is something that has happened. We just don't have proof of that. Okay, so body fossil formation. This is best for species that have a durable skeleton, be it an exoskeleton or endoskeleton, or that they have hard parts. But that's not enough just for them to have hard parts. They also need to have lived in an area where rapid burial was likely. Okay, so our first type of body fossil, unaltered remains. This is going to include bones, teeth, shells. These items retain the original composition and structure. Okay, so dinosaur bones. Yes, those are exciting finds, and I'm very happy for all the dinosaur bones that we have found so far, and hopefully, I'm sure there are others out there we haven't found yet, hopefully on most of the continents. Okay, so unaltered remains would also include those frozen mammoths in Russia, mummies, and you know, not all mummies were made on purpose by ancient Egyptians. So creatures, or even humans, can become mummified if they just happen to pass away in the right conditions, where you have dry air, arid environment, and what happens is that the soft tissue shrivels, and then it is then not so likely to break down by organisms. Unaltered remains also includes insects trapped in tree resin, like in the original, what were those movies? Jurassic Park, like in the original Jurassic Park movie. I don't know if they touched on that so much in the remake with Chris Pratt. I'm not sure about that. But in the old one from the early 90s, that's a good movie, the first one anyway. Okay, so insects trapped in tree resin or amber, anything that might get trapped in a tar or oil seep, like the very famous location, the Rancho La Brea tar pits in Los Angeles. Yes, downtown Los Angeles. They haven't paved over everything. The La Brea tar pits are there, and it is a tourist destination, and that is on my bucket list. And an example of a beloved animal found in the tar pits, saber-toothed cats. All right, we are moving. How long is this video? I have no idea. It's not really showing me. It's okay. 9 minutes, 18 minutes? No idea. Okay, so this other board, and I may have to play around with where I filmed from to try and minimize, yeah, I'm not going to be able to sit down, try and minimize the glare. All right, I guess that's okay. Here, trying to minimize the glare. All right, so body fossil types continued. So number one was unaltered remains. Number two, altered remains. In other words, it's not quite exactly the organism. Well, you don't quite have everything that was there when it was alive, okay? Altered remains. Several types here. First type, permineralization. What happens here is that you lose some of the original material as replaced with minerals. So it's the addition of minerals to pores and cavities in bones, shells, and wood. And some of your original material remains. Our second type here, B, is called replacement. What happens here is that minerals completely, 100% replace the original material. Examples would be petrified wood. In the case of petrified wood, it's very heavy and it feels like a rock, because really it is. It's microcrystalline quartz that replaced the wood as the wood was being predated upon by organisms. As the wood was going away, the quartz replaced it, and it takes on its shape. And you don't have any wood, so the petrified wood can be very old, and you don't have any actual wood left, but you can still tell what kind of tree stump that was. Petrified wood is really, really cool. We have some in our collection here. Okay, again, I'm gonna have to move around, and let's see what to do about the light glare. Okay. C, our third type of altered remains, carbonization. This is neat. You're basically making a carbon film. Okay, so volatile organic material leaving a carbon film imprint. So in other words, you may just have a carbon, and it'll be black, it's dark, it's carbon. So like a black print of, say, leaves or insects. You don't have any part of that leaf or insect left, just the carbon, but you have the shape of it, and you kind of, well, you can figure out a lot about what it looked like from that. Okay, D, molds. So when a buried remain, like say a shell, an oyster shell, dissolve and leave a cavity or void, that is a mold. Now, in parentheses, this is really meant for the folks in the Earth History lab, because Dr. Farley is going to want you to know the difference between an external mold and an internal mold. So there's a little bit here in parentheses. I forgot the other outer parenthesis. That's okay. A little bit here about the difference. So a shell outline, just leaving that void, but you can tell it's in the shape of a shell, that would be considered an external mold. If something hollow left, okay, something that was hollow, you have the outline of something that was hollow, that would be an internal mold. And we'll just leave it at that. Okay, for our class, for our exam, I'm not going to ask you to know the difference between external and internal mold. Of course, any questions you have, you can always consult the textbook. You can always just Google and find you a reliable site. And they might have all kinds of pictures of the difference between external mold and internal mold. Okay, and then our last type here, E, casts. So casts are related to molds in the fact that you start with a mold, some kind of cavity or void, and it gets filled in with sediment. Okay, so in the case of making a cast type of altered remains fossil, you have sediment or minerals filling in the cavity with a different material. Again, people in the lab are going to see all kinds of these. In the lecture, well, I may hold some things up for us to look at. Okay, so we're moving around a little to get rid of the glare. Okay, so I have a line drawn here in purple to denote that we are now finished with discussing the types of fossils, or the types of body fossils, and we're going to move on to some different material to finish up chapter 5. Principle of fossil succession. Okay, this is important. This says that unique fossil assemblages change and they succeed one another through time in a regular and determinable order. Okay, what does this mean? It means, again, that we've been studying fossils for hundreds of years. I'd say at least 300 years. Anyway, if you go back to when they found the first fossil, they probably talk about that in your textbook somewhere, I would imagine. So we've been studying these fossils for a very long time, many, many decades. And we have a good outline of the different organisms that existed at different times. So these assemblages are distinct and unique, and they do change throughout time as new species arise and some species go extinct. All right, now moving on, we're going to talk about 3 different units: lithostratigraphic, biostratigraphic, and time stratigraphic. So these are ways that we can break up the sedimentary material into groups. So the lithostratigraphic unit is based on rock type, lithology, which just means rock type. So it's based on rock type or lithology, and the primary example of a lithostratigraphic unit would be sedimentary formations. Now we do talk about this in the video lesson for chapter 6, which many of you maybe have not watched yet. But we may, I don't know, we might have talked about the Castlehane limestone sooner. The Castlehane limestone is a very distinctive limestone that we find down in the Wilmington area and as far west as Rocky Point, say along I-40. That is a sedimentary formation, and that is also a lithostratigraphic unit. Okay, another way that we could divide up our sedimentary material to try to make sense of it and put it into some kind of context of Earth time would be using the biostratigraphic unit, which is based on fossils. And then we can also use the time stratigraphic unit, which is based on the geologic time scale. All right, moving on. Just a little bit of material here. Again, I'm going to try to keep this. It's so hard to tell what the time is on this. I think we're not even 20 minutes yet, so that's okay. This chapter didn't take us quite as much time as I thought it would. Okay, yeah, I can't sit because the glare. Let's go like this. Okay, correlation. Correlation has to do with having access to different sedimentary sequences, vertical sequences of rock that are spaced out across a region. Okay, and then trying to match them up. So matching up rock assemblages across different areas using both lithology, rock type, and fossils. There's a good possibility that we will do a take-home quiz dealing with correlation. I already have one invented. We'll see how many, it just depends on how many take-home quizzes I'm going to give you guys. I probably should give you as many as I can because that's a good chance to get a grade that's not an exam grade. We'll see. You will have a few. Okay, next topic, index fossils. Not just any fossil is an index fossil. So index fossils are very useful in relative dating, as in putting different rock units in order, but without necessarily knowing an exact age for that rock unit. So it's very useful. Index fossils help us figure out relative dating of sedimentary rocks, because we can't generally get a radiometric date on sedimentary rocks. So index fossils must be distinct and easily recognized. They must be geographically widespread, so they were in many different places on the planet at that time, and they must have a short geologic time range for existence, meaning, you know, if a fossil that lasted for, or a species rather, that lasted for 500 million years, that's not going to make a good index fossil. So there's a couple of examples here. And on the PowerPoint slides for Chapter 5, I hope to, at some point in this semester, get to a point where we can take a few minutes, maybe, on some of these chapters and look at some of those PowerPoint slides.